Hello everyone. In this video, we're going to talk about the Stokes theorem. So this theorem is basically a three-dimensional version of the Green's theorem. If you remember, the Green's theorem says that this circulation of a vector field, where we're integrating a vector field over a simple closed curve C, it's the same as the double integral of the curl of the vector field, where we're going to integrate on the region D that's enclosed by this curve C. Now, the Green's theorem, it only works if this vector field F is a two-dimensional vector field, and this curve C is a two-dimensional curve, so that the region D enclosed by it is a region in the xy plane where we can do a double integral for it. Now, this is Stokes' theorem. We can have the vector field F to be a three-dimensional vector field now. And our curve C would also be a three-dimensional curve C, right? So the parameterization for this curve C is going to have three components where we have x, y, z. Each coordinate is going to be a function of time t. And for this kind of circulation of a vector field over a closed curve, now because it's in 3D, it's going to enclose a surface S instead of a two-dimensional region D now. So think about my picture here, right? For example, let's say this is my surface S. It's a curved plane. Now for this surface S, its boundary would be this edge here. That is my simple closed curve C, right? So this surface integral of the curl of a vector field. Remember, a curl of a vector field is always a vector as well. So that's also in 3D, right? So we're looking at the flux of the curl vector cross a surface S, which is the same as the circulation of the vector field itself along the closed curve C. So that's the Stokes theorem. And something to be a little bit careful about here is, again, the direction, the orientation matters, right? Otherwise, you might have an additional negative sign. So in the Green's theorem, if you remember, we always define our curve C to go counterclockwise so that those two expressions match. Now for Stokes' theorem, because our curve is in three dimensions, it's a little bit more complicated. Our surface, it already have a orientation, right? So let's say that, for example, for this surface S, I'm going to choose the upward orientation. Okay, so let's just say all the unit normal vectors are pointing up, which means that my boundary C now, it should be in positive direction for these two to be matched. And when we say positive direction now, what we really mean, this is going to be a little bit long, is that the surface would be to the left as we follow the positive direction of C, and our head is toward the orientation, this unit normal vector direction. Okay, so just imagine you are walking along this curve C, right? If I follow this arrow direction that I have drew here, if I'm standing right here, right, on the curve, now I'm standing on this curve. My head needs to be towards the normal vector direction. So I'm standing upward on this curve. And if I follow the direction C here, my surface is to my left, right? Which means this is a positive direction we want. However, if we turn the orientation to the other side, so let's assume that all our normal vector now, right? Let me change the color. If we assume we're going to have downward orientation, so all my normal vector is pointing downward, then when I'm standing on the curve and walk along the curve C, now I should be standing really head down as well. And if I'm standing head down and walk along the curve C in this direction again, you can see that way my surface would be to my right instead of to my left, right? So this will not be the positive direction of the curve. We need the curve to go the other way clockwise, right, to match with the downward orientation of the surface. Okay, so because both of the surface and the curve, they have directions. So now we have this way to make them match. Now if you look at the second surface here, this is a upper half of a sphere for my surface. For this surface, the boundary of it is just this circle on the bottom, right? And now again, if I assume that my sphere has a outward orientation, then as I walk on this circle C, to make sure all the time the surface is going to be to my left, I should walk counterclockwise again, right? So when I'm standing here, my head again is toward the normal direction, and normal direction should be coming out of the screen now, right? So I'm standing this way out of the screen, and if I walk to this counterclockwise direction, the surface is always to my left, right? If we turn our orientation of the sphere to be inward direction, then the positive direction of my curve C would be the clockwise direction, so that those two match. Okay, so this is just a way to make sure the two directions match, then this Stoke's theorem is true. Now let's look at some examples on how we really compute this kind of integrals using the Stoke's theorem. So the Stoke's theorem basically tells us we can evaluate a line integral to find the answer for a surface integral, right? Or we can evaluate a surface integral to find the answer to this line integral. And depending on which one is easier, which one is harder, now you can choose either one of them. The answer is going to be the same. So I'm going to show you both ways to compute these two, the line integral and the surface integral, and then you can decide which one is the better one to use. I have a vector field here, F, that's y, negative x, c, right? And then my S is the upper half of the unit sphere again, right? So that's my second picture here. My S is this upper half of the unit sphere, which means my C is this circle on the base. That would be a unit circle, right? And it's oriented outward, so just like my picture. Now we want to compute both the line integral and the surface integral. So for the line integral, Remember, the formula for the line integral, the basic one, is that we need to figure out what the parameterization of this curve C is. And the C only depends on one parameter, t. Once we know t is from A to B, then we can turn this line integral into a single integral about t. Right? So in this line integral notation, my ds is that tiny little part of the curve, which is this tangent vector of the curve. So for this part, if we want to evaluate this line integral according to its definition, then first thing to do is to write a parameterization for this curve C, right? And because my sphere now is a unit sphere, which means my radius is 1 everywhere, so my C is actually a unit circle, just by looking at the picture. And for unit circle, right, we know how to write our parameterization. We use cosine t and sine t. Right? And since this is on the base of the sphere, where it would be c equals to 0, right? Everything else is above c equals to 0, so my c is just 0. Okay, so that's my first part, and we know to have the complete circle, my t has to be 0 to 2 pi now. Right? And notice here my r, even though it's a two-dimensional circle, I need 3 components because my vector field includes that c, right? So I do need to write both x, y, z components for this curve. Once you have this, the rest is just the same as what we have been doing before, right? I plug in my r into my f, so y is sine t. Negative x would be negative cosine t, and we know c is 0. I need my r prime, which is derivative cosine t is negative sine t, derivative sine t is cosine t, derivative 0 is 0, and then by our definition, we need to do a dot product, right? So compute the dot product between them. I have sine t times negative sine t, right? So that's negative sine squared t. Negative cosine t times cosine t, so that's negative cosine squared t. And by Pythagorean identity, if I take out a negative sign here, we can simplify this to negative 1, which means my line integral, this circulation we're trying to find, is just the integral from 0 to 2 pi on this function 1. I'm sorry, negative 1. Right? So I know my final answer after integrating this would be negative 2 pi. Right? So in this example, the vector line integral is not too hard to compute. And note that we would not be able to use the Green's theorem for this one because my vector field f is a 3-dimensional vector field here, right? It's not just f1, f2, so the Green's theorem we learned before will not work. But we can compute this vector line integral just according to the definition. And now, for the Stoke's theorem, this vector line integral should be equal to the surface integral of the curl function of the vector field, right? So now let's compute the second one to see how complicated or maybe easier that one is. Let me change a color. We're going to find this flux of the curl of this vector field across my surface S, which is the upper half of this unit circle again. Upper half of the unit sphere. Now my F is y, negative x, c, right? But we're going to find the curl of it because that's our integrand now. So remember, to find the curl of a vector field, we look at ijk2 components, right? And these are just notations to say we are going to take partial derivatives on each component of my vector field f. And again, my f is y, negative x, c. So let me put down them here. Y, negative x, c. Right? So I know for my I component, we're going to do these two diagonals, the partial derivative of y with respect to z, which is just 0, minus partial derivative of z of negative x with respect to z, which is still 0. Right? So my I part is really just 0. And for my j part, now for j part, we're going to do these two, right? So partial derivative of z with respect to x, again, that's a 0. Partial derivative of y with respect to z, again, that's a 0. So my j component is also 0, right? This one, it's pretty easy to find the curl because there are a lot of zeros, right? I made this example easier so that it will save us some time to find these answers. And then the last one, for k component, I need these two diagonals. So partial derivative of negative x with respect to x would be negative 1, right? Partial derivative of y with respect to y would be positive 1, but we need to subtract them. So my curl that we need to integrate for this vector field is just 0, 0, negative 2. Okay? And we are doing this surface integral. So remember how we do vector surface integral? Right? So my vector field now, this is what we're integrating. It's not f, right? It's the curl of f. That's our 0, 0, 2. So our formula for this flux of the vector field across the surface is that we're going to turn it into a double integral over the region D now. And my first step is that I'm going to plug in my parameterization of the surface into my vector field, right? But my vector field is 0, 0, negative 2. These are constants, so there's nothing to plug in. So you can just leave it like that. And for my ds part now, for a surface integral, vector surface integral, the ds depends on the normal vector. We know that needs ru cross rv, right? And we need a dot product between the vector field, plugging the surface with this normal vector, and then we can integrate about u and v. Right, so that's our formula, which means that we need to find the parameterization for this surface first. And for our problem, again, right, we had the picture. The surface is just the upper half of this unit sphere. So we know we need to use the spherical coordinates, right? We did this several times already now. For spherical coordinates, because it's a unit sphere, we already know my rho is 1. So my x would be rho, which is 1, sine phi cosine theta. My y is rho, which is 1, sine phi sine theta. My c is rho, which is 1 again, cosine phi. Right? That's my spherical coordinates for x, y, z with rho is 1. And because it's the upper half, my phi is from 0 to 2 pi. Pi over 2. My theta is from 0 to 2 pi. Okay, so now that's my r, and my r is in terms of phi and theta, which means the partial derivative we're going to do here now is about phi and theta. It's not about u and v anymore. right? So let's look at the partial derivatives quickly, and these were actually done in class already, so I'm just going to write down the answer again, right? Just be careful about so many different expressions. We're taking derivative with respect to phi first, where we assume theta is constant. Then we take a derivative with respect to theta, so we assume phi is constant. Then we're going to do the cross product again. Right, and the cross product again needs the ijk2 terms. My first one is these two subtracting each other. That would be 0 minus a negative sine phi squared cosine theta. And then my j would be those two again. That's a 0 minus a positive part, but I have a minus in the front, so it become a plus again. That's sine squared phi sine theta. And then my k part, that's where we do these two, and these ones are longer. I have cosine phi, right? I have cosine theta. There's two of them, so I'm going to write sine phi first, then cosine squared theta, minus these two. That's again cosine phi, sine theta. I have two of them, so that's sine phi, sine squared theta. And this is the part where we have a minus, a negative, so it becomes positive. Then we can use our Pythagorean identity by factoring out sine phi, cosine phi. So we have cosine squared theta plus sine squared theta, which is 1. So this is gone. Right, so that's my cross product, and then the dot product we're doing is this vector field, the curl 0, 0, negative 2. Right, if there's any x and y in there, we need to plug in again our x, y, z. Right, but now we only have numbers, so we don't need to worry about that. We're doing dot product of 2, 0, 0, negative 2 with this cross product we just found. Right, and notice that this cross product is the outward orientation that our problem wants. Right, if you look at our problem again, it said that this sphere is oriented outward. Right, then that's something you will have to check, otherwise you might miss a negative sign in your answer. And for our cross product here, which is the normal vector we're using, if our phi is between 0 to pi over 2, right, then all of these terms are positive, so we are pointing in the outward direction in the first quadrant. Right, if my theta and the phi, theta is elsewhere, then it would be pointing the other way. Right, but the key is these are all positive now because phi is from 0 to pi over 2, so it's always upward. Which means it's the outward for my surface. Right, so now doing the dot product, so multiply corresponding components together, those are all zeros. All we have is just negative 2 cosine phi sine phi. Okay, which means that this surface integral we're doing, it turns into a double integral now. My integrand is just negative cosine phi sine phi. My variables are phi and theta. My phi is from 0 to pi over 2. My theta is from 0 to 2 pi. And to integrate something like this, inside about phi, we can do a u sub, right? If my u is sine phi, my du will cover that cosine phi part. So we're just integrating negative 2u, which would give us negative u squared. So for the inside, I have negative sine phi, then squared. And I plug in phi is pi over 2, plug in phi is 0, then subtract them. If my phi is pi over 2, sine pi over 2, that's 90 degree would be 1, right? If I plug in 0, that's 0. So inside, I just have a 1. Negative 1. And then integrate this with respect to theta from 0 to 2 pi. Again, would give us negative 1 theta, plug in 2 pi, plug in 0, then subtract. Our final answer is negative 2 pi again. Right? So overall, both of the vector line integrals and the vector surface integrals gives us the answer negative 2 pi for this integral, right? And it makes sense because the Stokes theorem tells us they are the same thing. However, you can see in these computations for this vector surface integral, because we have a sphere, the parameters are kind of complicated, so it took a while to compute this whole thing, right? Especially we have to do a cross product, then the dot product. And for the line integral here, if we just integrate over the boundary of the surface, because my boundary is just a circle, so it ends up to be a lot simpler now.